tonight in my talk. It's a great pleasure to welcome back Dr. Lurie, and he'll talk about non-abelian concrete duality.
All right, thank you very much. So, what I would like to talk about today is a generalization of statement of Poincare duality. So let me begin by reviewing for you the usual form. So recall the setup. So let M be a compact oriented manifold. Dimension D. And Poincare duality tells you that the homology and cohomology of M are the same. More precisely, a choice of orientation of M determines a canonical isomorphism in the homology of M, let's say with integer coefficients in some dimension star, and the cohomology in dimension D minus star. So what I would like to do first is sketch for you a proof of Poincare duality, which is going to highlight some features that I want to replicate in the more general form of Poincare duality that I'd like to talk about. So there are several hypotheses for this theorem, but of course the most important of them is that M is a manifold. And that's a local condition on M. It says that M looks locally like Euclidean space of dimension D. So if you want to understand this statement, you might start by trying to understand what happens in the local case, namely when M is equal to R to D. And then you, for the statement that I gave you, immediately will object that unless D is equal to 0, this doesn't satisfy another hypothesis, which is that M is compact. But there's a generalization of Poincare duality to non-compact manifolds. We'll just erase this word compact at the cost of, on the right-hand side here, working not with the usual cohomology of M, but with compactly supported cohomology of M. So when M is compact, this is the same statement from before, but now it's a statement which makes sense in the case where M is a Euclidean space. And in the case of a Euclidean space, the homology of M is easy to understand. Right? M is contractible, so its homology is the same as the homology of a point. So this looks like Z in degree 0 and 0 otherwise. So in that case, this Poincare duality statement is really a calculation of the compactly supported cohomology of Euclidean space. This is just telling you what the compactly supported cohomology of Euclidean space has to look like. This has to look like Z in degree D and 0 otherwise. So let's say you believe this statement, and you would like to prove Poincare duality in general. So the idea is that you should be able to get from knowing Poincare duality locally to knowing it globally by articulating some local to global principles that are satisfied both by homology and by compactly supported cohomology. So what do I mean by local to global? I want to think not just about the homology and cohomology of M, but more generally the homology and cohomology of arbitrary subsets of M, or arbitrary open subsets of M, let's say. So it's just some notation. I'm going to write script U of M to mean the collection of open subsets U contained in M. And then I want to think of homology and compactly supported cohomology as giving me functors from U of M to category of graded abelian groups. So what does that mean? Well, they're functorial in the sense that if you have an open set U contained in a larger open set B, then you get a map from the homology of U to the homology of B, and from the compactly supported cohomology of U to the compactly supported cohomology of B. And in particular, M contains any open set, so you have maps from the homology of all the open subsets of M into the homology of M. Now, we want to sort of zero in on the open subsets that look like Euclidean space of dimension D. And in that case, these maps will not be very interesting, right? Because an open disk is contractible, its homology is concentrated in degree 0. So if you want to articulate a local to global principle that really lets you build the homology of M from the homology of small open subsets, you don't want to work at the level of homology itself. Instead, what you want to do is work at the level of chains that represent homology classes. So for every open subset U contained in M, I'm going to write C star of U to mean the singular chain complex of U. So this is the chain complex such that if you take its homology, you get the singular homology of U. And similarly, I'm going to write C star compact of U for the compactly supported singular cochain complex. So this is another chain complex, and when you take the homology of this one, you get compactly supported cohomology. And these are, again, functors of U. So if you have an inclusion of some open set U into a larger open set B, then it induces a map from singular chains on U to singular chains on B, and compactly supported cochains on U to compactly supported cochains on U. So now I want to state a property that this functor has, or that both of these functors have. So let me say it in words, and then let me say a little bit about what it means. So just cite this as a fact. Functors U goes to singular chains on U, and U goes to compactly supported cochains on U, are what you might call homotopy cosheaves. Which means they satisfy a certain local to global principle. So let me not give the definition of this in general or in complete detail. Let me tell you one thing that needs to happen to be a homotopy cosheave. So, or sort of the main thing that needs to happen. So the main thing that needs to happen, let's say for singular chains, is that if U and B are open subsets of M, then we can say something about singular chains on the union of U and B in terms of singular chains on U, singular chains on V, and singular chains on the intersection. So if you have open sets U and V, then U union V is built by gluing U and V together along their intersection. You want to say that something similar happens at the level of chains. And the precise statement is that this is what's called a homotopy pushout square of chain complexes. If you don't know the word homotopy pushout square, well, let me tell you what it means in this specific example. So all of these maps are actually injective. And this diagram gives you a map from chains on U plus chains on V into chains on the union of U and V. And this is a map from the pushout along chains over the intersection. And to say that this is, if you wanted to say that this was a pushout square of chain complexes, what you would say is that this chain complex is isomorphic to this pushout here. And to be a homotopy pushout means, in this case, not that this map is an isomorphism of chain complexes, but that it's a quasi-isomorphism, meaning that it induces an isomorphism on homology. Iso on homology. So I claim that even if this specific terminology is not familiar to you, the consequence of this, or the content of this statement is familiar to you. This is exactly what gives you Meyer-Vietoris sequences in homology. So a corollary and morally an equivalent form of this statement is that in this situation, there's a long exact sequence which relates the homology of the union, the homology of U plus the homology of V, and the homologies of the intersections. Star minus 1 of U intersection. So you have some exact sequence like this, and this is morally the content of the statement that homology, that these cochain complexes form a homotopy cosheaf. So you have a Meyer-Vietoris sequence in homology. You also have a Meyer-Vietoris sequence in compactly supported cohomology. And those give you some kind of local to global principles that tell you how to compute the homology of a big manifold, or the compactly supported cohomology of a big manifold, in terms of the homologies of some smaller pieces that it's made out of. So let me just restate this. So C star and C upper star are compactly supported. Satisfy this condition of being homotopy cosheaves. And this gives you a way to compute the homology of a big manifold in terms of the homology of any basis of open sets. So let me write down a consequence of this. So let script U0 of M, contained in script U of M, be the collection of all open disks. Collection of all open sets that are homeomorphic to a Euclidean space. So the assumption that M is a manifold is exactly the assumption that there's enough of these, meaning that these form a basis for the topology of M. So then what I can do is I can consider for each U in this basis of open sets the singular chain complex of U. And I can take a direct limit over all U look like an open disk. And when I say direct limit, I want to do this in the homotopy theoretic sense. I want to take what's called a homotopy direct limit. Let's say it's a direct limit colimit. What's called a homotopy colimit. And the fact that this thing satisfies Meyer-Vietoris sequences tells me that when I do this, what I get is going to have the same homology as C star of M. And similarly, I can take the homotopy colimit over all open disks of the compactly supported cochains on U. And this can be identified with the compactly supported cochains on all of them. So now I want to combine this with our local analysis. Right? Our local analysis tells us when U is an open disk, then compactly supported chains on U is a very simple chain complex. It has homology only in 1 degree, and therefore it's quasi-isomorphic to just the chain complex Z concentrated in degree 0. And similarly, the local calculation of compactly supported cohomology says that these chain complexes satisfy something similar. There's Z placed in homological degree D. So now, what does this tell you? Well, locally, you can identify these chain complexes. And when I say identify, I mean you can write down a quasi-isomorphism between them. It just amounts to writing down an isomorphism of Z with itself. And if you do that in a functorial way, meaning a way that's compatible with including one open set into another, then you'll get an identification of this homotopy colimit with this homotopy colimit, and therefore a quasi-isomorphism between these chain complexes. And that's exactly what Poincare duality is telling me that you have. And your ability to choose these isomorphisms compatibly is just another way of saying that your manifold is orientable. So the upshot of this discussion is that you can think of Poincare duality as made out of two pieces. The first is a local calculation that tells you, in the case of a manifold, the compactly supported cohomology locally has a very simple form. And the second is a local to global principle that doesn't have to do with manifolds. It can be stated as saying that singular homology and compactly supported cohomology both have some sort of co-sheaf behavior. So what I would like to do in this talk is extend these ideas to the setting of cohomology with non-abelian coefficients. So let me say a little bit about what I mean by that. So let me first remind you of one way that you can define the cohomology of a nice topological space. So cohomology in the world of sufficiently nice topological spaces is a representable function. So for a nice space M, for example, a space with the homotopy type of a CW complex, you can identify, let's say, the cohomology of M with coefficients in an abelian group A with a collection of continuous maps from M into topological space typically denoted by KAN up to homotopy. So here KAN denotes what's called an Eilenberg-MacLane space. And what that means is it's a space whose homotopy groups have a very simple description. So KAN is a space where the homotopy groups look like the abelian group A in degree n and 0 otherwise. So you can prove that there always is such a space, and it's unique up to homotopy equivalence. And one of the articulation of the fact that it's unique up to homotopy equivalence is in the homotopy category of spaces, it has this universal property that mapping into an Eilenberg-MacLane space is just computing the cohomology of the space that you're mapping out of. So maybe some examples. If you're not familiar with this, if you ask for a KZ1, you're asking for a space whose fundamental group is Z and which has no higher homotopy groups. So, simple example of such a space. If you ask for a KZ mod 2, 1, you're asking for a space whose fundamental group is Z mod 2 and has no higher homotopy groups. One way to build such a space is to take a sort of infinite dimensional version of real projective space, meaning a direct limit of RPNs as n goes to infinity. And there's an analogous statement for complex projective space of infinite dimension. That's an example of a KZ2. But there are not many other examples where these spaces have names other than KAN. These are what my advisor would call designer homotopy types, meaning they're not spaces that you meet by thinking about geometric problems. They're spaces that you introduce that play a sort of formal role in homotopy theory. They're characterized by a universal property. So let's say we wanted to talk about non-abelian cohomology. So what would that mean? So here's one take. non-abelian cohomology would be if you wanted to allow A to be a non-abelian group here, well, you could contemplate a KAN only in the case where n is equal to 1, right? The homotopy groups of a space are always abelian groups, except in degree 1, where you're talking about the fundamental group. The fundamental group doesn't have to be abelian. So for G any group, you can define a notion of H1 of M with coefficients in G. And this is given by a set of homotopy classes of maps from M into an Eilenberg-MacLane space KG1. So this is one description. There's some other descriptions which maybe are easier to think about. So if M is connected, this is the same thing as homomorphisms from the fundamental group of M into G modulo conjugacy. And another description of it is that this is the collection of principal G bundles on M up to isomorphism. So this is one thing that you might mean by non-abelian cohomology. But I would like to consider a more general notion, a more liberal notion of non-abelian cohomology in this talk. So instead of thinking of non-abelian cohomology as mapping our manifold or our space M into an Eilenberg-MacLane space, I'm just going to think about mapping M into any space. So more generally, if X is any space, we can make a sort of useless definition, which is I'll define the cohomology of M with coefficients in X to mean just the collection of continuous maps from M into X mod homotopy. What I've already denoted over there by brackets M comma X. So let me write down a sort of table of analogies that will be useful to keep in mind. So comparing the sort of abelian and non-abelian versions of various notions. So what does the cohomology of X in the usual sense depend on? This depends on, let's say, an abelian group A and some integer n, which tells you the degree of the degree in which you want to take cohomology. And the thing that's going to play the role of both of these over here is a choice of just an arbitrary space X. And the way that to get non-abelian cohomology to specialize to usual cohomology is to take X to be an Eilenberg-MacLane space. So once you've specified what your coefficients are, then you can talk about Hn of, let's say, a manifold with coefficients in the abelian group A. And the thing that's going to be analogous to that over here is just homotopy classes of maps from M into the space X. Now, when we were talking about Poincare duality, it was useful to think also about a compactly supported variant of this. So you can talk about the compactly supported cohomology of M with coefficients in A. And in order to make sense of an analog over there, let me assume that X is equipped with a base point. And then I can talk about compactly supported maps from M into X, meaning maps from M into X such that outside a compact subset of M, I require that everything goes to the base point. Now, over here, I wanted to talk not just about cohomology groups, but also about the chain complexes that compute them. So we were talking earlier about compactly supported cochains on M with values in A. And the analog of this over here is to think not of homotopy classes of maps from M into X, but the space of all maps from M into X. And if we're talking about the analog of compactly supported, we'll take compactly supported maps. So this is the collection of all compactly supported maps from M into X viewed as a topological space. And now over here, we had Poincare duality, which told us that the homology of M, or the cohomology of M with coefficients in A was related to the homology of M with coefficients in A. And what I would like to do in this talk is to tell you how to complete the right-hand side. How to make sense of some notion of homology in this context such that it can be identified with cohomology via something like a Poincare duality. So let's try to break this down the same way we did in the abelian case. So in the abelian case, we broke understanding Poincare duality into two steps. First, understanding what happens locally, and then articulating some kind of local to global principle. So let's start by analyzing the local case. So an example would be, let's take M to be Euclidean space of dimension D. And then we can talk about compactly supported maps from M into some target space X. So these are just maps from Euclidean space into X that are compactly supported, meaning outside of some large ball, everything goes to the base point of X. In this discussion, everything in sight, I really only care about it up to homotopy equivalence. So up to homotopy, it doesn't actually matter how big that ball is. If I have a map that's supported in the ball of radius infinity, then I can always shrink it so that its support lies in a ball of radius 1. So this can be identified with what's usually denoted by omega d of X, which is just a space of maps from, let's say, the unit disk of dimension D into the space X, where you demand that the boundary of the disk, the unit sphere of dimension D minus 1, goes to the base point of X. So I want to think of this as the analog of computing the compactly supported cohomology of Euclidean space. The analog of that here is you just take the d-fold loop space of whatever your target is. Now, the interesting part is going to be what happens to the local to global principle. So note, if you can think not just about compactly supported maps from M into X, but compactly supported maps from open subsets of M into X. So if you consider the construction which takes an open subset of M to the space of compactly supported maps from U into X, this defines for you a functor from open subsets of M to topological spaces. What am I saying? I'm saying, well, if U is contained in some larger open set V, then there's a construction which takes a compactly supported map from U into X to a compactly supported map from V into X. And that construction is just send everything outside of U to the base point, which gives you something continuous under the assumption that your original map was compactly supported. And so motivated by our previous discussion, we can ask if this functor satisfies a local to global principle. So question. If you look at this functor that takes U to compactly supported maps from U into X, is it a homotopy cosheaf? Well, soon as you understand what this question is asking, you can immediately see that the answer is going to be no. Right, so let's consider, again, what happens when you have two open subsets, U and V, contained in X. So then you can look at compactly supported maps from the intersection into X, compactly supported maps from U into X, compactly supported maps from V into X, and compactly supported maps from the union into X. And one of the things that this question is asking is whether or not this diagram of topological spaces is always what's called a homotopy pushout square. Now, if you don't know what a homotopy pushout square is, let me just tell you, this is not going to be one. One of the things that we would have to prove in order to verify this is that every connected component of this space was either in the image of this map or the image of this map. So, or more concretely, given any compactly supported map from U union V into X, we would be saying you can modify it by a homotopy so that its support lies either in U or in V. And it's easy to come up with examples where this is not true. So the answer to this question is no. So now let's ask why. Like in the abelian setting, we asked an analogous question and the answer was yes. So what's different here? What's different is that we're asking in this setting for a homotopy cosheaf in the world of topological spaces, which behaves very differently from the world of chain complexes. And it's specifically different because in the world of chain complexes, you can just add maps together. And in the world of topological spaces, you can't. So remember that the homotopy cosheaf property in topological spaces had to do with some kind of Meyer-Vietoris sequence. So let me write down what it would be saying. The compactly supported cohomology of U union V participates in a Meyer-Vietoris sequence which relates it to the intersection of U and V and say the compactly supported cohomology of U plus the compactly supported cohomology of V. So the exactness of a sequence like this was the kind of thing that made this true in the abelian setting. And what this exact sequence is saying is that if you have a cohomology class on the union of U and V, which satisfies a certain vanishing of a certain obstruction, then you can write it as a sum of a class which is supported on U and a class which is supported on V. And the word sum is important there. You don't know from the exactness of this sequence that everything satisfying an obstruction either comes from U and V individually. So it's important that in ordinary cohomology you're able to add things together. So if you ask the question, why not? Meaning, why isn't the answer to the previous question yes? And the answer to this is we can't add. Specifically, we can't take a compactly supported map on V and a compactly supported map on U and add them together to get a compactly supported map on the union. You can't do that in general. But there's one situation in which you can do that, and that's when U and V are disjoint from each other. Note that U and V are disjoint, the intersection is the empty set, then compactly supported maps from the union into X. To specify such a map, you just separately have to specify what it's doing on U and on V. There's no compatibility to consider. So this looks like compactly supported maps from U into X cross compactly supported map from V into X. And if I think of this as going from right to left, this is giving you some kind of partially defined addition on compactly supported maps. But you're only allowed to add maps whose domain is disjoint. Okay, so now that if the construction that takes U to compactly supported maps from U into X were a homotopy cosheaf, well, then we could have, let's say, then we would have been able to write just what we wrote down in the case of chain complexes. We could take the homotopy colimit of compactly supported maps from U into X. Now, every compactly supported map from U into X gives us a compactly supported map from our entire manifold into X. And that's compatible with restriction in U. So there's always a map from this homotopy colimit to compactly supported maps from M into X. And now, if this was a homotopy cosheaf, then we would be able to say that this map was a homotopy equivalence as long as I took enough U's, meaning any collection of open sets which form a basis for the topology. So here we can take the homotopy colimit over this collection of subsets of M that look like Euclidean space, as we did before. We would have that this map is a homotopy. But this isn't how it works. This thing is not a homotopy cosheaf, and this map that I've written down is not a homotopy equivalence. But you can fix it if you somehow correct for the ability to add maps together. So the problem with this map, in some sense, is that it isn't telling you anything about how about your addition law on maps. Because if you take a map which is supported on one disk and a map which is supported on a disjoint disk and add them together, then you get a map which is no longer defined on a disk. It's defined on a subset of M that looks like a coproduct of two disks. So an idea is to fix this by allowing more open sets. And I just want to allow the smallest number of open sets that I need to consider in order to contemplate this addition law on maps. So let me define U1 of M to be the collection of all open sets U contained in M such that U is homeomorphic to a disjoint union of finitely many disks. So you can again contemplate what happens if you take compactly supported maps on this larger collection of open sets. Each of these spaces of compactly supported maps maps to compactly supported maps whose domain is all of M. And now the theorem is, let's call this non-abelian Poincare duality version 1. The theorem says the following. So let M be a D-manifold. And let X be a space which has some connectivity. Specifically, we need it to be D-1 connected. And this map is a homotopy equivalence. So I want to do two things with the rest of this lecture. I want to first convince you that this deserves to be called non-abelian Poincare duality, that it really feels like some version of Poincare duality in the non-abelian setting. And the second thing I want to do is to tell you why this might be a useful thing to know. So let me start with the second part. So let's ask the following question. Why is this useful? Or how could it be useful? So let's assume that M is compact. Let's actually give ourselves a whole blackboard. Right on. So let's say that M is a compact manifold. And in that case, compactly supported maps from M into X just means all maps from M into X. And what this theorem is saying is that you can build the space of all maps from M into X by gluing together spaces of compactly supported maps from, well, let me say U1 disjoint union U2 disjoint union UK contained in M, where each UI is homeomorphic to a Euclidean space. And here you would get the compactly supported maps from the union of these disks into your target space X. And now we did a local calculation that tells us how to think about this mapping space, right? If I was mapping just one disk into X, then what I would see is that that mapping space looks like the d-fold loop space of X. And in this case, I'm mapping k disjoint disk into X, and I just get a product of k copies of the d-fold loop space of X. So what this theorem is giving you is a mechanism for computing the space of maps from M into X, which is a priori something complicated and hard to understand. So we don't a priori know much about the topology of M and X, and this mapping space is something that tells you about how the topologies of M and X can interact with each other. And this theorem is telling you that you can build that mapping space out of pieces where the structure of the pieces is totally independent of M. Each piece depends only on X. And the way that the pieces are organized, the poset that indexes them, depends only on the manifold M, which has nothing to do with X. So you sort of break the problem of understanding this mapping space, which allows M and X to interact, into some description where M and X are not interacting. I mean, of course, they are interacting because even though these pieces are individually independent of the structure of M, the way they fit together when you form this diagram reflects the structure of M. But if you were interested in computing some invariant of the space of maps from M into X, and that invariant had the feature that a decomposition like this would give you a method of calculation that didn't depend on how the pieces were fitting together, then this would be a great thing to know. This would let you compute your invariant of this mapping space just by computing the invariant of these local pieces. And that's how we're going to use it. So let's say we can use this in lectures 3 and 4. And when I say this, maybe I should put that in quotation marks, because this is a statement in topology, and what we're actually going to use is an analog of this statement in algebraic geometry. But we'll use this in lectures 3 and 4 to sketch a proof of Bayes' conjecture. So that's one reason that you might want to know this statement. Now, another question that you might ask, so here's one question. Another question is, why is this Poincare duality? And there's a couple of ways that you can answer this question. So one is that this is Poincare duality in the sense that when you specialize to the case where X is an Eilenberg-MacLane space, you can take this statement and can prove Poincare duality from this statement and vice versa. But that's maybe not super convincing because the proof is not much harder or not really any easier than just proving Poincare duality directly, or proving that compactly supported cochains form a homotopy cochain. Right? This is a replacement in the non-abelian setting for the fact that you have Meyer-Vietoris sequences. In compactly supported cohomology, you can deduce the existence of those Meyer-Vietoris sequences from a statement like this, but that's maybe not the most efficient way to do it. So another answer is, well, in this statement, actually, let me leave the statement. So in this statement here, we're comparing a right-hand side and a left-hand side. And the right-hand side is this space of compactly supported maps from M into X. And I told you earlier that, well, at least if you take pi 0 of this space, this is what I call the non-abelian cohomology of M with coefficients in X. Or more specifically, it's the compactly supported variant of that. So the right-hand side is something that you should think of as like cohomology. And so another version of this question is, why should you think of the left-hand side as like homology? So how is this direct limit compactly supported map from U into X like homology? And one answer is, well, it's like homology, but not the homology of M itself. Instead, it's really the homology of a closely related object called the Ron space of M, which I'll now describe for you. So definition. If M is a manifold, or we define this more generally, the Ron space of M is defined to be the collection of all non-empty finite subsets S contained in. And I'm going to view this as a topological space. So let me describe the topology for you. So first, I want to observe that if I take a bunch of disjoint open sets, U1, U2, so forth through UK, contained in M and disjoint, then I can take the Ron space of U1, the product of the Ron spaces of each of these UIs. I can identify this with a subspace of the Ron space of of M. So this can be identified with the collection of points in the Ron space of M with the property that, well, first, I want to say it's a finite subset of M that I can get by taking a disjoint union of non-empty finite subsets of each of these open sets UI. So that is true if and only if F is contained in the union of all the UIs, and also S intersect UI is not empty for each I. So I'm going to topologize the Ron space of M by declaring that these form a basis of open sets. So let me write script U Ron to be the collection of all open subsets of Ron M that belong to this basis of the form Ron U1 cross K. And actually, let me even be a little more specific. Let me demand that each UI is connected. So in defining this topology, I don't need to allow U1 through UK to range over all open subsets of M. It suffices to allow them to range over any conveniently chosen basis for M. So for example, when M is a manifold, I get the same topology if I just take open sets of this form where each UI is an open disk. Or, same argument, I can allow each UI to range only over connected open subsets of M. So now let me define script F. This is going to be a functor from these special open subsets, the Ron space, to topological spaces. So I just have to tell you what I'm going to do on each one of these open sets, Ron U1 cross dot dot dot, cross Ron UK. And I'm going to take that to be the collection of compactly supported maps from the union into my target space X. So here's an equivalent version of this theorem up here. So theorem, let's call this non-abelian Poincare duality. Version 2. And it's this functor, which is defined on open subsets of the Ron space, satisfies a local to global principle in the naive formulation that we gave earlier. So functor F is a homotopy cosheaf. I want to explain why these theorems are related to each other. So let's assume that M is connected. So if we assume that M is connected, then the Ron space of M is an example of one of these special open sets. Right? Then Ron M itself belongs to this class U Ron. So I'm allowed to evaluate my functor F on the entire Ron space of M. Now I told you that the Ron space has a basis of open sets of the form Ron U1 cross dot 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 cross Ron UK, where U1 through UK are disjoint open disks. And if this functor, if you believe version 2 of non-abelian Poincare duality, F is a homotopy cosheaf, that means it satisfies a local to global principle. You can compute its values on a big open set in terms of its values on any conveniently chosen basis of open sets. So theorem 2 gives that F of the Ron space of M can be computed as a homotopy colimit of F on Ron U1 cross dot 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 cross Ron UK, where U1 through UK are disjoint open sets. Or sorry, disjoint open disks. And this is almost exactly what theorem 1 is saying, right? By definition, what is F on this? This is the space of compactly supported maps from the disjoint union of the UK, two i's, into X. And this here is the space of compactly supported maps from M. Theorem 2 is telling you that this map is a homotopy equivalence. If you're a stickler for the details, it's not saying exactly the same thing because the posets indexing these diagrams are slightly different, but those are details that you can iron out. So theorem 2, by applying it in this particular case, gives you a proof of theorem 1. And with some care, that argument is reversible. is if you know that theorem 1 is true, not only for the manifold M itself, but for every open subset of M, then by going through this reasoning, you can deduce that this F is actually a homotopy cosheaf. That this argument applied to open subsets of M is exactly what you need to check once you make all the proper definitions. Okay, so how much time have I got left? Not much. So let me just say, I want to make the argument that this second formulation of the theorem maybe has a better case for why it should be called non-abelian Poincare duality. It's telling you that you can compute this space of maps in some sense as the homology of a certain sheaf, although that sheaf is not, well, cosheaf I should say. That sheaf is not defined on the manifold M itself. The price of having a theorem like this in the non-abelian setting is that you have to work locally on the Ron space of M rather than just on M. So in the next lecture, we're going to talk about algebrogeometric versions of an algebrogeometric incarnation of this idea, and it's really version 2 of the theorem that appears most naturally in algebraic geometry. So this Ron space actually, well, at least the terminology of the Ron space was originally introduced to discuss an analogous construction in algebraic geometry. So why don't I stop there? Thank you very much.
Questions?
So, in your thinking of this left-hand side as a homology theory, is this some version of the Dalton theorem?
I think that if you I think I see what you're asking, and I don't immediately see the best way to answer it. So let me,
Play.
since I'm being videotaped.
Okay.
Other questions? Okay, so Tony is going to lead a dinner tonight, and should
5:45.
people still talk to you, or is it all filled up?
No, if people want to come, they should come.
Okay. And I'm going
If
to
they
do
haven't
likewise
already.
tomorrow. Let Tony let me know if you'd like to join.